I don't think you actually need an example for this one, but I'm going to do one anyways. The reason why they're going to be called, or why they are called, exponential model equations is because they model situations where things grow or change exponentially. Like a lot of population stuff is modeled by exponential equations. We maybe saw that, or you guys maybe saw that in Algebra 2. But let's solve this, okay? Okay. So the first thing that I'm going to do is notice that this is an initial value problem because I have initial conditions. When x is 2, y is 1, or f is 1. But I don't care for this notation, so I'm going to change it. I'm going to change this to dy dx, and it's going to be, well, f would be just y. So there we go. I'm going to change it to that. Then I can use my techniques for separating. This is a separable differential equation. How do I know that? Well, it's a function of y and something else. Well, I mean, normally it would be a function of x, but we have a constant. So we can put actually the constant on either side, and I'm just going to leave it over there. So what I'm going to do is I'm going to multiply by 1 over y. And then I will split up the differentials. So I have the 1 over y piece with the dy, and then the dx is going to be over there with the negative 6. So then I have that, and of course, I mean, you guys, hopefully, you know how to do this already. There's nothing new. You take the integral of both sides, and then what do you get? You get the natural log of the absolute value of y, and that's going to equal negative 6x plus c, and then you're going to exponentiate both sides. We have the absolute value of y, but as soon as we exponentiate this side, we will have y being positive anyway, so it doesn't hurt us. But I'm going to exponentiate both sides. So now I just get y. I mean, technically it's absolute value of y, but this is always going to be positive, right? No matter what I plug in there, I can't get a negative out of an exponent unless the base is already negative. So I'm just going to leave it as regular y. And then we talked about this before in the other videos, but I'm going to show you once again. So that's fine. That's one way to write it. Or I can write e to the negative 6x times e to the c, right? Because if you have the same base, you add the exponents. But this e to some constant is still just some constant. So I'm going to change that to c. Some people get really confused about that. Again, I'm going to go over it again and again. If I have e to the second power, that's still just some number. I mean, it's some nasty decimal, but it doesn't matter. It's still a constant. So what is normal is to change that to a capital C and put it out in front as a coefficient, and then it looks nicer. And then I don't have any like weird exponents to look at. So I have that. That's the general solution to this differential equation. However, we have initial conditions that I'm going to use. So I'm going to plug in those initial conditions, and those initial conditions would be f of 2 equals 1. So that means when I plug in 2 for x, I get out 1 for my y. So I'll have 1 equals c times e to the negative 6 times 2. Well, that's just e to the negative 12, or the same thing as c divided by e to the 12th. If I multiply both sides by e to the 12th, then I have solved for c. So there's a couple different ways you can write this. Normally, we change this and leave it like that. So then, I guess, but here we have the same base, so on multiple choice it might look different. So I'm just going to write it a couple ways. But and I guess when they have the same base, it makes sense to actually just write everything in the exponent. But you'll see what I mean right now. So I take my general solution, which is that. No, it's not that. Where was it? here, that's my general solution. I'll take my general solution and I'll plug in c. So y equals e to the 12th times e to the negative 6x. But I already have the same base, so might as well just write e to the or like 12 minus 6x, because that's the same thing, right? I add the exponents. 12 plus a negative 6x is that. So there you go. That's your particular solution to the initial value problem, which is, I mean, it didn't say it's an initial value problem, but it is an initial value problem, and that's it. That's all you got to do. It's the same as that we've always been doing. So these are both ways that you can write it. Just recognize those are the same thing, and good day.